You
Um,
mean this one?
yeah, so there's two screenshots. The first is the question, the second is her
Mm-hmm.
work. I just have a question about part B.
Mm-hmm.
So it gives you three different scenarios where
Mm-hmm.
you're looking at a like a solid conductor. It's like a solid,
Mm-hmm.
like
Mm-hmm.
rectangular
Mm-hmm.
um conductor, and
Mm-hmm.
you're comparing the different like electric fields, the current
Mm-hmm.
density, the current of like the front and back panels compared to like the side panels compared to the top and bottom panels. And
Mm-hmm.
for part B,
Mm-hmm.
it says greatest current density. So
Mm-hmm.
I understood part A because essentially electric field is just V over D.
Mm-hmm.
So it says the potential difference V is
Mm-hmm.
uniform, so the V is going to stay the same for all situations. So
Mm-hmm.
the only thing
Yeah.
that change is D, like the
Mm-hmm.
distance between those
Yeah.
two states.
Mm-hmm.
So you're able to find out that like, oh, like the top and bottom one, the difference is L, so that's going to be the smallest, meaning the electric field is going to be the greatest.
Mm-hmm.
So I understand the ranking is 312,
Mm-hmm.
but it says greatest current density, and
Mm-hmm.
her reasoning was J is equal to I over A, so the current
Mm-hmm.
density is equal to the current divided
Divided
by
by
A.
cross-sectional area.
Yeah, so I was confused because it makes sense, I guess, because if J is proportional to, if the current density is proportional to the current and the
Mm-hmm.
current is proportional to electric field,
Mm-hmm.
technically the two rankings should be exactly the same. That's her reasoning.
Mm-hmm.
But the thing is, the current density is equal to the current divided by the area.
Mm-hmm.
Um, so I thought the area, because the area changes for each scenario, wouldn't that have an effect on the ranking as well? Because then I calculated the different currents
Mm-hmm.
for each scenario, and I got I calculated the different electric fields for each scenario because it's V over D.
Mm-hmm.
So like the first scenario, it would be V over 2L. The second one would be V over 3L, and the third one would be V over L. Like those are the different electric fields for
Mm-hmm.
each scenario.
Mm-hmm.
Then I did that because it's proportional to the current. I did that divided by the area.
Mm-hmm.
So the area would be for the first one would be like 3L. So if you did V over 2L divided by 3L, it's essentially V over 6L. So I calculated the different current densities for each scenario using the electric field divided by area, and I got the current density is equal for each one. So I'm a little bit confused on how she got the.
Why? I mean, the is there something you came up with yourself, or is it the way to solve this problem in this way is given by your school teacher?
Wait, sorry.
How did you come up with the way to solve this problem? I mean,
So like my way of solving the problem is
yeah.
it's just using like inference from like part A. We know the electric field. We know the electric field is equal to V over D. So and the V is the same for every scenario. The only thing that's changing is the D. Like the first one, the D is equal to 3 is equal to 3L. Second one, the V is equal to or the first one is equal to 2L, the D is equal to 3L in the second one, and then D is equal to L on the third one. And then she said in the second part that the current is proportional to the electric field. So what I did is I just solved for all the electric fields and I divided by the area of each one to solve for J. It's just like plugging in different equations. And I got that 3 is equal to 1 is equal to 2.
So the electric field, you said that current is proportional to electric field,
Yeah.
right?
And
So
that's what my teacher. Yeah.
the I is in actually in principle V I is proportional to V of R in conductor. So the R is actually characteristic actually parameter of any conductor. So V is constant value, and R is depend on the size of conductor, right? So R is the conductivity times the area, right? So I just kind of confused the way you actually so like V, you divide V by the length of L. So you assume that the two end facets produce the electric field, and their strength is inversely proportional to their distance. So you came up with the field strength out of the relationship, right?
Yeah,
And
this makes
then the
well.
V divided by distance between the two faces of the conductor in that orientation. So you got that field, and you assume that the current is proportional to the electric field. I mean, just kind of rephrased what you described to me. So then you divide by the cross-sectional area to rank the current density, right?
Yeah.
So in that, if that is the case, so let's take a look. Um, number one, H of L and 2L. I mean, the way you asked me the current density, the field along that direction, potential. Hmm, I should take, I can come up with the resistivity is, so basically R is the, I have to look back. Can you help me to actually, I had to refresh my memory because I think you got to use that the resistance rather than the electric field. So R is conductivity times what? Do you? I can't remember. Like I should take a look at it. Um, so hold
Oh,
on.
R is equal to P times L over A.
All of A
Or are you talking about are you talking about like resistive?
resistance, right? Resistance is function of the resistivity, right?
So resistance is equal to resistivity multiplied by the length divided by the area.
Okay, okay. So that's the what I'm looking at. So I got oh shoot, I should remember that. Okay, right there. So oh, gotta write it down. So I think that so that because I is the V of R, right? So V is constant. It applied to all the direction, all of the directions. So the V should be constant value. You have and then you have to divide by R and divide by cross-sectional area to rank the current density. So let's take I should remember. So can you just say that resistance is, I don't remember. Oh, shoot.
Resistance is resistivity multiplied by the length divided by area.
Okay, multiply length divided by area, right?
Yeah.
So can you use that approach? Can you use that the formula to solve this equation? I think that's better way to solve this one rather than using the electric field configuration because now you're dealing with the conductor, not actually capacitor, right? So there's some kind of constant current along that the conductor. So because now let's see the V of R, the R and conductivity and L of A. A is the cross-sectional area too, right? So let me write it down. Can I hold on? So let me give you the better way to solve this problem rather than using the electric field configuration. I mean, this is I think this is I think the better way. I mean, so hold on. Where is my? Oh, oh, that's not this one. Okay, got it. All right. So hold on. We share my screen. So you have all three of all three direction. Oops. Okay, right there. So all three direction, right? X, Y, Z, and you have this shape of conductor. And you said all three direction X, Y, Z code axis, they all just have they biased with the same potential difference, right? B, E,
Yeah.
B, E, B. So if you look at this cross section in maybe in Y, and there's current flow like that, and I is B of R, and R is conductivity times L of A, right? And plug that into this formula, then I is V of low times L of A. I think better to use this definition because if you do that, then that should be V times A over low times L. L is the distance, but as you already showed me, L should be different depending on the direction of your current flow, right? So now if you divide that both sides, then that should be I of A, which is J, and that should be B over low L. So this is pretty straightforward because your current density only proportional to the electric field, I mean the voltage between those two, size of the rectangular box, and the conductivity and L. But conductivity is the same for all the other directions. So basically, your current density J only depend on the length of the length between those two faces. Does it make sense? This might be straightforward. So now let's just pick up. Well, let's just go back to your question again. Where is it? Hold on. Right there, right? So let's pick up the L, 2L, 3L. Okay, let's just go back to the previous problem. Right there. All right. So now let me redraw it. So you have L, 2L, and 3L, right? So now, as I said, the current is V of low L A, and that is B times A times, B times A over low of L, which is L is actually, let's just change that as the S. S could be L, 2L, and 3L. So if you're looking at two faces, this one and this one, then current across that this y direction, and this is x, and this is z. So the y direction, then that should be 3 times cross-sectional area is that L times 2L, and divided by low times S is what? 3L. Okay, that is for y direction. And Ix is B times A is what? 3L times L divided by low times 2L. And Iz is B times, what's that? B times, let's see, cross-sectional 2L times 2, 2L times 3L divided by low times L. So now you can compare 3Ix, Iy, Iz. But if you want to compare the current density along the three different directions, then you have to divide it by cross-sectional area, which means you have to move this one to the denominator underneath of the current. So that should be V over low 3L, which is 1 over 3 V of low L. And this one, Jx, in this one is actually Jy, and Jx is, what's that? That V of 2 low L, and this might be I, and Jg is Ig divided by A, so that should be V over low L. So let's just length, which one is highest number? So like I think G is highest current density, and this one, x, the current density along x-axis is second, and the first one, the IY, the vertical direction, current along the vertical direction should be third.
Wait, where did the 3 in the numerator go for the x?
Which one?
3L times L?
3L times L? That's area A. So in order to actually calculate the current density, you have to divide by A in both sides. A just cancel out, then only leave A over low 2L. Current density.
Hmm.
So do you want me to rewrite it? We can
No,
do it.
I
Do you understand? Does it make sense, or do you want me to rewrite it?
no, I think it makes sense.
Okay, so the current proportional to the cross-sectional area, but current density only depend on the length of the conductor. So because V is IR and V is constant value, so I is V of R. So only depend on the resistance along that direction.
Wait, for the IZ, the L in the denominator, why wouldn't it be
No,
3L?
yeah, that's what I'm saying. I mean, this is actually should be yeah, this one JG divide by A. We got to divide by A, right?
So the L,
JG. A is 3L times 2L. So
the
that's then cancel from
the L in the denominator multiplied by the resistivity. Like, why is that just regular L?
this one. You're
No,
talking about JG,
the L multiplied by the resistivity in the IZ.
IG. Yes, 3 times 2L. I mean 3L, 2L divided by low L because L is distance between these two, right?
Oh, so it's essentially just the same thing as calculating the electric field.
Yeah, but this is straightforward. It's just yeah. No, so that is you stay with the configuration in Ohm's law, V equals IR. I'm not saying that you're wrong, but I'm saying that this is kind of like a straightforward because you stay with the more rigorous way to solve this problem with Ohm's law. So basically, let me rewrite it. Basic formula: I is V of R, and J is I of A, which is V A R, right?
Yeah,
So
okay, that makes sense. Yeah.
okay, so does it change? Does this way change your answer or?
No, I think the easier way to go about it though is my teacher just said that the electric current density is just proportional to the current because of their relationship is just the current is just equal to the current density multiplied by the area. So you know the current density is basically proportional to the current itself, and you know the current is proportional to the electric field. So no matter what, the
Current
ring,
is proportional to electric field.
yeah. So because you know the electric field ranking, then you know the electric field ranking is going to be the same for the um electric current density ranking as well.
Yeah, but I bet you if someone asks you this kind of problem, this is probably more kind of like logical way rather than conceptual approach because it's based on the more rigorous math. So you just stay with Ohm's law and plug that all the parameters into the formula, and then you have a very clear answer out of the basic formula. Okay. So back to that your question, does it explain what you are puzzled?
Yeah.
Okay, okay, okay. So basically, that the area just so the current density has nothing to do with the cross-sectional area. Current itself is is proportional to the cross-sectional area.
Yes.
Okay, because the density, just like mass density, um, mass density law has nothing to do with the volume itself. Okay, so similar with the, you can maybe just put it that way, just like, you know, density itself has it like a unique property of material itself, has nothing to do with the volume or cross-sectional area itself. So anyway, hopefully that help you just understand. Okay, and let's get back to, where is it? This one. All right. Did
I
you?
think I'm like reading my questions again. I think I understand
Mhm.
the problem. Let me see if there's a question. Um, I think the main thing that I'm confused
Mhm.
about is um how you set up the okay, for the one on the second page,
Second page, this one.
yeah.
Oh,
Uh,
this one.
no, like the one right below the last one we were at, the second page, page two.
Page two. Oh, I think it is the end of the page.
Like up, like page two.
Page two. Oh, okay. This one or one above this one.
Yeah, that one.
Okay.
Oh, wait, no, the one above, sorry.
This
Yeah,
this
that
one.
one.
Okay.
Um, I'm a little confused because how do you know where to the EMFs they give you are unlabeled. You don't know which one's the negative side, which one's the positive side. So do you just assume which side it's going to be on? Like which direction the EMF is going to go?
Oh, I mean like which direction the EMF produce positive charge and which direction has negative charge.
Yeah. I think
Oh,
my teacher just arbitrarily put plus negative on the EMF. I'm not really sure what she did.
well, no, actually, the large bar is always indicating a plus sign, positive direction. Short short bar actually always indicating the negative side, minus bias.
Hmm.
That's convention. Like
Hmm.
convention, it's a symbol.
Okay. And
So
then
here is like a large bar. You said that's the plus and minus sign was given by your teacher, right? The teacher just said that's plus and minus sign on the EMF, right?
yeah,
So the plus sign always with the large bar, like a long vertical direction, larger bar, and the shorter bar is always, you know, direction for the negative bias. That's kind of convention. It is we normally use that convention to assign, current floor. So you can just think of the current coming from the large bar of EMF and just circle back to the negative side, which is the shorter bar.
but the current for EMF is opposite to the electric field of the EMF, right? Because electric field always goes from high potential to low potential. Um, so
Right?
if you put like a positive,
The electric field is just always plus to the minus. So the electric field direction is always from positive charge to the negative charge.
yeah,
Not high to low, it's like positive to the negative.
so it would be opposing the direction of the EMF.
Opposing
Because
or
the EMF direction is going from the negative to positive. So the electric field itself is going from the positive to negative, though.
um are you talking about like, maybe I confused you the probably the word you used, but EMF is the battery always produce current from positive to the negative. the current flow.
But
Okay.
when you have like a positive and a negative side, the electric field, like you said, goes from the positive to the negative side. So while the current goes from the negative to the positive, as you can see like in the drawing, the electric field of the battery itself goes in the opposite direction, from the positive to the negative.
So, okay, let me just redraw it and maybe have to clarify the question. So let me draw the picture. Assuming you have battery connected to electric circuit right there, right? And usually that this one is positive, this is negative. And then your question is,
That the I know the current in the battery, it
yeah,
always goes from the negative to the positive. It's gonna go out the positive and come back to the negative.
yeah.
But if you look at the battery itself, like the two
Uh-huh.
different parts, the
Mhm.
electric field within that battery is gonna go from the positive to the negative because that's conventional. Like electric field always goes from like the positive to the negative. So it's gonna oppose the direction of the current of the battery,
Are you talking about the battery or is it capacitance?
the battery.
Battery? Well, internal battery itself has um their own sign, but there's direction also like a negative to the positive field because that's a way to actually produce the current. So there's not it's not like a capacitance, I mean capacitor.
Okay, I think I'm just mixing up the two.
Yeah,
Capac
this now you can this is not this connection. This current flows all the way across like this battery too. So from minus to direction. The capacitance is different. There's disconnection, discontinuity. So one side charged plus, and that current goes along the circuit, and this is negatively charged. That field produced from positive to the negative, like this. That's capacitor. But the why this is battery. Battery is actually just continuous current flow. Electric force actually produce that the current flow across that the actually battery too itself. So battery itself is also kind of resistor. So produce the continuous current flow along that the circuit, internal circuit of battery too.
hmm
The field, if there's field, I mean, I like a little bit um, puzzled with that the idea of field inside of actually battery itself. But if you think there's a field existing in the battery, then that direction should be same as the current flow because the electrons well actually that is another actually convention too. Normally we assign the current direction is opposite to the electron direction. So actually, electron is going along the opposite direction of current in physics. But the same thing, in the same way, that's actually, uh, in the battery itself, also we assume that current is same direction of electron. I mean, the opposite direction of the electrons.
Yeah, that makes sense.
So basically, you can think of a battery as just wire too. Part of the wire is this continuous current flow along the battery, but capacitor there's physical discontinuity, disconnection. So there's like two plate, as you know, that produce the electric field while the one plate positively biased, the other is negatively biased. As time goes by, then they produce the electric field opposite direction of current flow.
Yeah, that makes sense.
Okay.
I think for my other questions, let me see. Um,
Let me go back to right there. Okay.
for the one above that one,
This one.
yes.
Okay.
How do you know the direction of current one and current two and current three? Is it just is it like arbitrary? I think what my
Oh,
teacher
yeah.
said is that you just put a direction that you think the current will go. You can put it in left or right, and at the end you solve for the current, and if it's
Mhm.
negative, you just
Yeah,
flip the
yeah,
um. hmm.
yeah. Your teacher is absolutely right. You can actually pick and choose the direction of the current as you want. But one thing I want to tell you, still, the current should comes out of the battery in positive, um, the symbol. The all the current should just comes out of the battery and then flows back to the battery too. But you can just think of like I1, uh, and I maybe like I you can set up the I3 the opposite direction to the I1 or same direction of I3. But once you solve the problems out of the loop rules and the junction rule, if current value is negative value, that's what I think I only told you last session. If this negative value comes out of your calculation, then that means the direction of your current is opposite direction. So you have to reset the current direction based on the value out of equations.
Yeah. But for the drawing that my teacher did, she
Mhm.
did the EMF is going to the left, and then she decided that the current of I is gonna just go up or is going to the right. So wouldn't what you said is like the current is get going out of the positive, so isn't it more logical to choose that the current I is going to the left as well? I don't know why she chose it's going to the right.
Which current are you talking about? Like I2 or I3 or
Uh,
I1? I1?
Yeah, because the EMF direction of the current is going to the left of
Mhm.
EMF 1. Then she
Mhm.
chose that the current I is just going to the right, which
So, okay, what value did you get? I1 is positive value or negative value?
it didn't ask to solve for
Hmm.
the values. It just asked for
So I guess once you solve the equation out of the junction rule and loop rule, you may have a negative value I from the I1 because that. Well, here's the thing. Actually, this your three batteries, they're pointing in the same direction. So depending on the potential, net potential difference between A and B, that current flow will be also changed because your net potential difference between those two and um, the current value will be determined by that the um, I mean the overall actually the the equation. So basically now if you set up the I1 in the opposite direction of the orientation of the EMF1, then I guess you will get the negative value of I1 because that is just opposite direction and it's supposed to have positive value. But I got maybe take a look at it. But you may want to just solve it. Okay. I don't know.
I think ultimately it doesn't I think the for the different currents it doesn't matter like which direction you set them at originally as long as your junction rule is correct to solve for the
Yes, 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 yes. I agree with you. I mean, as I said, that's um, you can set up your current direction arbitrarily as you want, but your total current should be consistent to meet the junction rule. Okay, so if you have two current into the junction, that comes into the total current in the other wire, then you should just stay with the same net current. Otherwise, you just not gonna get the right answer because that produced the wrong current numbers, the number of the current, wrong numbers of the current floor. So now, let's see. You assume that I'm just trying to give you the feedback based on what you draw in the picture because in order to get you the more accurate, feedback, I have to just solve it myself. But based on what you draw in the picture, you just assume the I2 flowed right to left, right? And the I3 is flowing upward, just like I1. So in that configuration, I2 plus I3 should be same as I1 because two floors comes into the one floor, right? So I3 plus I2 should be same as I1 as long as A and C are connected.
Yeah.
Yeah, understand? So basically, what I'm trying to point out, that's like, or maybe you can also do this like if you hold on, okay, only hold on, right there. So now you draw connection like this, right? So hold on. So you have A and C, and you assume there's I2, I3, and I1. So if you just connect it, then obviously I1 should be I2 plus I3, right? That junction rule.